Welcome everyone. My name is Theja Tulabandhula. Thank you so much for giving me the opportunity to present this work. The title of this work is Making Recommendations When Users Experience Fatigue. This is joint work with a first year graduate student at Johns Hopkins, Yunjuan Wang. So, as you all know, recommendation systems Recommendation systems are a core part of many commercial offerings like Netflix, YouTube, Spotify, or many of the other service systems that you may have interfaced with. And they're very critical for the success of these platforms and companies because they impact the engagement of their users and therefore the revenues of the companies. And there are many approaches, many solutions, recommendation systems. And one of the key things that you want to get to in a recommendation system is relevance, and relevance is impacted by many different aspects. For example, your user could be a new user, in which case you're facing a cold start problem. You may want to model your users to be of certain types or have certain propensities, and so you want to get the modeling correct. You may want to show diverse recommendations, or you may also want to show recommendations which are of high value to you as well as the customer, and so on. um, Here is an example, and it's going to be a running example through the stock. So here's a screenshot of YouTube. You can see a video being played at the center, and towards the right is a sequence of videos from top to bottom, which are going to be recommendations. So in this case, the recommendation is not a single video, but actually a sequence of videos in a linear order. And here's another example. This is an older interface of Netflix, but you can see there's a bunch of movies being recommended in the bottom two rows here. And so there is a left to right ordering of these movies that are being shown to you as recommended items. So, given this context of what recommendation systems are and why they're important, let me jump to what is the goal of this work and what are our contributions. So, the goal of this work is to recommend a sequence of items over a period of time that are competitive to the best in hindsight under position and fatigue effects. So let me highlight a couple of phrases. First of all, we are in each period or each interaction, in each interaction with the user, we're going to recommend a sequence of items. Just like in the YouTube example or the Netflix example, it's going to be a list of things with order relationship between them. And so maybe there are going to be multiple interactions over a period of time. So maybe capital T number of interactions, and we may show different sequences of such videos or items. And then at the end of the day, we're gonna compare how did our recommendations fare with respect to a single best recommendation in hindsight. Okay, a single best sequence of videos in hindsight. And we're going to do that in the context where the user has certain propensities. So this is the modeling part, where the user has both position influence as well as fatigue, and as well as they experience fatigue. Okay, so these are some couple of preferences or properties of the user that we also want to capture. Okay, and in this context, we have two contributions. One is an algorithm. So we develop such a behavior aligned algorithm where the behavior is going to be something which can capture the position and fatigue effect. And we do this by adapting some well-known tools in this area. And the second contribution is we also obtain a tight regret guarantee for this realistic application setting. Okay. There's a lot of related work in this area, so I will not be able to really justify much of this work. But starting from the seminal work on multi-armed bandits, which is the foundational core, there's been work and also work on combinatorial recommendations. So basically, when you have sequences or sets of things to show together, and an amalgamation of both these, which are I guess loosely called combinatorial multi-armed bandit problems, where you care about regret, which is the metric of choice here, and also care about working with the combinatorial space of actions. Okay. And the last two sets of relevant literature areas are the one in terms of positional effect and the other one in terms of fatigue effect. And in fact, we're going to consider both these effects. So our work is quite related to these two last areas, and the key differences are either in terms of the model description, the model that we assume about the user, or in terms of the solution approaches, if it's the same model. Okay, and in particular, our solution approach is going to be based on Thompson sampling, whereas some of the other approaches, if it's the same model, have used optimism and uncertainty principle. So let me jump to what our user, how does our user respond to recommendations? So, and as well as the general context. The platform in each interaction with the user, so at a time period little t, recommends a subsequence of which is boldface S based on the items. Okay, it's a sequence of items which is represented by boldface S, and so let the items themselves be S1, S2 to S little m, where Sk denotes the item in the kth position. Okay, and for each of these items, the user has an intrinsic preference for this item, which is represented using a scalar uj, which is between 0 and 1. So what do I mean by intrinsic preference? If I did not show other items, and if I just showed one item as j, then this is the utility or some sort of a preference that the user has for this item. Okay. After viewing each item, and this is the fatigue part, the user can abandon the platform with a probability which is 1 minus q, which is strictly greater than 0. And there's a very simple abandonment model or a very simple fatigue model. It can be generalized further, but for this talk, we restrict to this setting. And so uj, one for each item, and there are capital N items, and we are only recommending maybe 3 items or 10 items. So little m is 3 or 10, for example. And uj's and q are the parameters in the system. And further, there are a couple of other parameters. If the user abandons, then the platform incurs a penalty c, which is greater than 0. So every time the person logs off, closes a tab, or signs off your subscription service, you lose $C, for example. And they select J and leave, then the platform gets a revenue RJ, which is greater than 0 and also known. Okay, and if they don't select an item J and move on to the next item, the platform gets nothing. Okay, so this is a simple description of how the user behaves. So this, given these parameters UIs and Q, we can compute two very succinct quantities. One is what is the probability that the user picks an item I if a sequence boldface S is shown. Okay, that's Pi of S. That denotes the probability of selecting item I in sequence S. Okay, and the second number is the probability of abandonment, which is if I show the sequence boldface S, then what is the probability that the user abandons the system. Okay. And with these two numbers, we can define an objective function, which is the expected utility. And the expected utility is just the weighted sum of these probabilities. Okay. And our objective as a firm, if we know the parameters of the user, which are U and Q, boldface U and Q, then we can just maximize this optimization problem, maximize for that sequence, which maximizes this expected utility under various business constraints. And these business constraints could be that, for example, an item I has to be always shown before item J in the order, or if item I and J should not be shown in a single sequence of recommendations, and so on. Okay, and this problem can be NP hard or easy depending on the constraints, but we don't focus on that direction in this paper. What's the difficulty now? The difficulty is that we don't know these parameters U and Q, and as usual in much of the multi-arm manual literature, and so we have to learn these U and Q just enough so as to minimize our regret and do well as the benchmark. Okay, the benchmark is going to be the sequence that maximizes this objective and maximizes problem 1. Okay. And let me jump to our result itself. So we designed an algorithm called SBORS. Okay, and the algorithm has this regret guarantee, and I'm just showing you a abbreviated theorem claim here. So over capital T rounds, the regret of algorithm SBORS is bounded as a term as a term which has these 3 terms. And if you focus each of these 3 terms, either the dependence on t, which is the horizon of the interaction, is sublinear in t, or it is also polynomial in the number of items. Okay, so either it's order n square or linear in n, and so on. Okay, And so this is the regret guarantee that our algorithm achieves, where let me focus on what the instead of so we'll not pass through each of these three terms, although I'll give you a little bit of intuition on how we get to this result. Let me just reinforce the definition of regret itself. It's the usual definition of pseudo regret that you would have seen in other papers. It's basically over t rounds, S star would be the optimal solution of that benchmark problem, the problem when you know u and q. So that is the utility, and so t times that is the one reference point. And every round t, little t, you show boldface S superscript t as your sequence of recommendations. So that achieves some utility with respect to the true parameters, and the gap between them hopefully is low and hopefully is bounded, and that's what we show in this theorem. Now, let me focus the next few slides on what is the algorithm. And the algorithm is actually just a variation of the Thompson sampling template. And let me recall what the Thompson sampling template is. It is a algorithm which maintains a belief on which action is good typically, and updates this belief based on taking some action and observing some feedback. Okay. In our case, in each round little t, we sample from a posterior belief, and in our case, the belief is going to be over the unknown parameters, boldface u and q. Okay. And the boldface you remember is the intrinsic, the vector of intrinsic preferences, and q is the abandonment parameter. So once we sample from here, we use those samples and solve these combinatorial problem to get a sequence of recommendations, and then just show that sequence of recommendations to the user. And once we show that sequence, then the user is going to respond by picking one of the items, or abandoning the system, or not doing anything. And given that feedback, we update the posterior depending on how the sequence fares. Okay, so let me focus a little bit on the feedback. So the feedback is actually very simple. It's a Bernoulli feedback, and to maintain our posterior belief, we can actually, just like in Thompson sampling, we can maintain a beta prior and or a beta posterior distribution on each parameter, for example. And if it's beta distribution because of Bernoulli feedback, you can always have some empirical statistics, summary statistics, like, for example, Ci of t denotes the total number of users who selected item I by time t, or Fi of t, which is the total number of users observing item I but not selecting it, and so on. Okay, these summary statistics can be used to parameterize your beta distribution. But now we deviate a little bit from Thompson sampling and do what we call correlated sampling. Okay, so first thing what we do is we don't want to maintain beta distributions, but we actually approximate these posteriors using Gaussian distributions, and this is actually kind of useful for our analysis. And so if you're going to maintain Gaussians, there's going to be two parameters, the mean and the variance, which we call it u hat I and sigma hat I, and they will have a couple of tunable parameters, alpha and beta. They are kind of not very important, but given these parameters u hat and q sigma hat of I for each item I, as well as the abandonment probability, what we're going to do is not just sample from these Gaussians, from each of these Gaussians, one for item, but do a correlated sampling. Okay, the important part of correlated sampling is what is the correlation level, and that's going to be this parameter r here. And we're going to first sample our capital R number of standard Gaussians, and then do simple transformations from given the empirical statistics and the samples to get some intermediate numbers u prime i's, and then take their maximum. Okay, so what these steps determine is, at the end of the day, we get a single parameter per item, for example u prime I, and the abandonment parameter q prime, but this u prime and q prime are all correlated because they're all dependent on the same R sources of randomness. Okay, and given that, so that's pretty much the algorithm. Once we have this correlated samples, given the samples, we solve for the best sequence given this estimates u prime and q prime, and show that and get some feedback, and keep updating the beliefs. And now, before I just give a quick intuition on the why the algorithm works, let me show you that the algorithm works in practice. So here are some simple simulation results where the number of items, or the number of videos, for example, is 30. and the abandonment probability is quite small. It's only 10%, and C, which is the cost for abandoning, is zero point 0.5. Okay. And boldface U is uniformly generated between a bunch of these intervals A, B, C, and D. And you can see how the as expected, regret is going to be hopefully sublinear in the horizon. So y-axis is the regret, and x-axis is the time horizon, and these are different runs. So different curves are just showing different runs of the algorithm, and lower is better. Okay, and each of these 4 plots. And next, I just want to quickly also show the dependence of the algorithm on various parameters of the either the instance-dependent parameters or the parameters of the algorithm itself. So, so the first plot on the top right, top left, is showing the dependence on if the intrinsic preferences are large or small, and then the next 3 plots, F, G, and H, are showing the dependence of regret as a function of the algorithm specific parameters. For example, the correlation level R, which is captured by this integer R, as well as the alpha and beta, which figure in these estimates U hat and sigma hat i's, which were the Gaussian approximations to the beta distribution, beta beliefs. So I will not talk about the trends. I mean, we can see that depending, I mean, the choice of these hyperparameters influences the performance of the algorithm quite a bit. But let me switch now to talk about what is the intuition for getting this regret bound. So in this particular application, or in this particular context, in this combinatorial problem, the way to handle a regret is to we saw the definition of regret a few slides ago. The way to handle to get a bound on this regret is to add and subtract a couple of terms so that we can get 2 terms. And what are we adding and subtracting? Remember, in the definition of regret, it's the performance of S star, which is the best sequence in hindsight with respect to the true parameters U and Q, and the performance of STs with respect to the true parameters U and Q. Now, what we're going to introduce is ST with respect to the sample parameters. Sample parameters U prime and Q prime, as well as S star with respect to sample parameters U prime and Q prime. Okay, so somehow you can introduce these 2 additional terms, and then focus on, and that somehow gives us a regret in terms, breaks the regret into 2 difference of 2 terms. And the first term is going to be small. So the first term is going to be related to S star and the sample parameters, and S star and the true parameters. Okay, and so we want to make each of these 2 terms small. So the first term is a function which depends on these correlation level, which is determined with the integer R. Okay, so this term is going to be small if at least one of the R sample leads to what is called an optimistic round. And an optimistic round is defined as that round in which a star, which is the best in is the benchmark sequence, has at least as much reward on the samples as a star itself would get on the true parameters. So a star is anyway opt on the true parameters, but it should do even better on the sample parameters. And the question is, in which rounds can this happen? Okay, if you choose R judiciously, then this can happen often, and this can lead to low value for the first term in the regret upper bound. Okay, and similarly, the other term, I'm not showing the terms here, but the other term can also be made small if the difference between the objectives parameterized by samples and the true parameters for ST is small. So now it's all about the argument being ST. ST is the opt for the sample U prime and Q prime, but it's not opt for the true parameters. But if you can make the difference small, then the other term, the other term will be small. And to do so, we have to just rely on the properties of the objective function. In this case, the objective function has reasonable monotonicity and Lipschitz properties to achieve this difference. Okay, and once you combine these 2 subparts, you can get a upper bound on regret, which I showed earlier. Now, so that's pretty much it. And so let me summarize what the contribution here is. We motivated the need for a particular behavior-aligned algorithm in recommendation systems design, and it can also be extended to other service systems, same ideas. We capture 2 effects, position and fatigue. We address how to learn the parameters of these effects while earning, and that's what makes the regret kind of bounded, upper bounded nicely. And the algorithm, of course, comes with a nice regret guarantee. There are lots of directions that can be pursued, just immediate directions that can be pursued. And of course, the larger context is to design such behavior aligned algorithms. The immediate directions could be that fatigue is not just within a single interaction, but also across interactions. And that means the notion of a state and so on. Maybe use reinforcement learning here. We also have not introduced context in this work, but contexts are something that can be brought in easily. But the more challenging thing would be to model users who exhibit multiple behavioral patterns simultaneously, not just position and fatigue, but other things like repetition effect, reference effects, and so on. With that, I will end. Thank you so much for your time.